This conference will now be recorded.
There you go. Hey, everyone, I just wanted to let you know that the Test and Validation Enablement Initiative is live on our OCP website. If you go to the website and you go to the top level projects, there's a drop-down menu there, and it shows up about halfway through the menu. God, I'm having a hard time with this. Right here, OCP 2021 Strategic Initiatives. And the TV&E or TVE initiative is right here. It's got Paul's name on it, the calendar is on it, the weekly calendar, and you can either click on each one of these and copy it to your calendar, or you can click the plus button and add the series to your calendar. These are in Central Time, so just a heads up, they won't reflect in your local time zone. You can subscribe to the mailing list or direct others to subscribe to the mailing list. And then, of course, there's a link here to the wiki. And the wiki has all of the past call recordings for anyone that is interested in listening and catching up. So as you guys decide to have more and more documents and more content here, let myself, Michael, or Paul know. Paul will be giving you admin access here as well, so that we can update the website, the wiki, and just let us know how we can help in making this. But now you have a place officially to direct people to if they're interested in joining this, or if you know of others that would be interested in joining this this work stream here. And with that, I'm going to turn it back over to Paul and stop my screen sharing, and he can go ahead and share his screen and get started.
One quick question, Arkna, concerning the document repository where it's not open yet. If this would ever become public, would we get one more pass to go through and sanitize some of the things we share here before they become public?
Absolutely. It's completely up to the group here. Nothing obviously everything here is public because we don't have any passwords or user IDs to get into any of our documents. So yeah, consider everything here public information and be discerning about what you post. Obviously we do not want any confidential information. We don't want any presentations that say proprietary or not for distribution on the handouts. We want to make sure that anything that's posted here is, open for everyone's eyes. There is a general understanding to everybody that comes to our website and within our working group that anything in the wiki is work in progress. So we treat it as work in progress. It has not been licensed. There's no copyright licenses, associated with it. It's pretty much work in progress. If you do, however, go to our main website and go under the contribution portal and into our contribution database, everything there has been licensed. So all documents have been licensed, all specifications have been licensed, all software has been licensed, and the license is in the document itself. So you'll see either it's a Creative Commons license or a copyright license or a contribution license agreement or something of that. So if someone wanted to to implement a spec or to use a spec, that is the final version that has been licensed by the contributors. And they won't have any patents asserted on them for using it or implementing it.
Okay, thank you. That's super helpful.
Yeah, but the wiki is kind of work in progress and fair game. And so highly recommend no confidential information on it. Paul,
thank you.
Back to you.
All right, thank you very much. Hey, morning, everyone. Thanks for taking the time to join today. I think we have a caller. Not sure who that is.
That would be it's up here. I just use the phone as a backup just in case the stuff drops off.
Okay, yeah. Cool. So I think we can pick up where we left off last week. There were a couple things on the agenda last week. We were looking at completing the PCIe spec. I think, Dan, you were going to share Jesus this week.
Yeah, I'll do a little presentation on Jesus.
So maybe we can get started with that. And then I think we had a discussion about BIOS testing and internally, and we're trying to get some input from the OSF team as well to whether we should kickstart the BIOS test process. So those are on the agenda today. So then, if you want to start with the Jesus presentation.
Sure, I'm trying to share. It says I need to be made a presenter to start sharing my screen.
Let me see if I can do that. There you go.
There we go. Okay, can you guys see that okay?
Yep,
Yep.
I can see just fine.
Yeah, so I wanted to talk a little bit about Jesus and how we use it at Google. Ultimately, one of the goals that we have here from this OCP forum is we want to start sharing some of our diagnostics, right? And the way we build diags at Jesus or at Google is it's difficult to separate them from Jesus in some ways, right? So moving on here. By the way, Jesus, Google System Manager, actually, I guess something along those lines. That's what it actually stands for. But historically, the way we've always thought about diags, I think, isn't that unusual. You know, we kind of decompose them into two things, like the synthetic load that we're putting on the machine. Not all diags have a load, but most of them do. And then something that's monitoring the telemetry of the machine or looking for certain events to happen, right? For us, that's been Jesus, right? The concept of a machine at Google, it used to be an Intel server back in the day, right? That's changed a lot. I mean, obviously, we have many, many different architectures now. Even the concept of what is a machine is starting to change, where we look at what we would historically call a node or a single server, to where we're looking at some of our machines now are more similar to what you would see in the supercomputing or high performance computing space, right? The advantage that this hardware abstraction layer has given us is not writing diags necessarily to the metal, is that we now have about 80 different diagnostics that work across all the different machines that we have, whether that be like a tiny TCP/IP offload accelerator all the way up to like a full server or even a large ML cluster, right? So what is Jesus? It's an RPC service and a CLI utility, and it basically gives us the ability to manually debug hardware via the command line. We get all the information about hardware, like its inventory, is it present, is it working, what are the capabilities. We get all the telemetry and errors from Jesus, right? It does some initialization and loading of kernel modules, along with some system init scripts that it probably shouldn't be doing, but it does. And then also, most importantly, it provides our hardware detection and abstraction layer, sort of what we call our through model for repairs and operations inside the data center. So I'll talk a little bit about what that looks like. So where does it live in the stack, first of all? So what I tried to put together here was sort of a system software stack where we have all of our different device drivers on top of the kernel or in the kernel. We have the kernel and the BMC. We have the kernels on server and storage. And then between our test and all of the Linux or operating system and BIOS, we have this layer here, Jesus. So this is kind of where it lives in the stack. And then above that, we have all our different tests that we run. And then above those tests, we have our applications. So what does that hardware abstraction layer look like here? Really, we break things down into these concepts. Basically, a board, which is like really a root device for us, right? It may contain 0 or more devices. It may have 0 or more connectors on it. Things plug into a board. Devices plug in. Devices can have sub-devices, right? Connectors are things that plug them together. It's not typically a bus when we call it a connector, right? That usually means like a physical connector, like with a stilt screen component, like J1, J2, whatever that happens to be, or a pluggable chip like a U1, U2, right? And then the cable. And some of our cables are electronically discoverable, and then some are inferred, right? So by the fact that these two devices are talking, we can infer the presence of a cable. So we put all this stuff together and we build something called a dev path, right? The dev path is sort of central to the way that all of our operations work at Google. Really what it is it's a unique way of identifying a device, a physical device that you could either repair or replace inside of a machine. And this is one of the most important things that we really get from Jesus. Jesus is the only way to really identify this, right? And look here, I just kind of gave some examples, like a DIM might be physical system 0, DIM 0, right? If you look at a SATA cable, this would be an example of an inferred device, right? We can see that, cable 22 attaches to drive 22, right? That's what a dev path basically is for us. How do we use Jesus? Generally, tests use Jesus in two ways. We use it to find all the parts that are in the machine that we want to test, and then we use it to get telemetry as well, right? So if you were looking for something like PCIe statistics, right? There are two approaches that we may take, and we've been talking about this a little bit. You could go and use device driver specific properties, which we do, but we typically expose those via Jesus. You may also use things that are a little bit more industry standard, like say the advanced error reporting registers, right? Like those are accessible via /zipss, but we typically get them through Jesus so that we have that commonality across different products. So the pros of this approach, and there's pros and cons for sure. The pro is our diagnostics are cross-platform, right? A lot of times, like our diag is a no-op when we get a new platform because of Jesus, right? It just works. It kind of abstracts away things that are complicated. One of the things that has always been complicated for diagnostics is sort of DIM error decoding, finding out like which DIM the error actually occurred on, right? Jesus takes care of a lot of that for us so that we don't have to have our diags have a lot of platform knowledge, right? And then finally, we get that common device model that's sort of the glue between our diagnostics, our repair system that we use in the data center, and then just our data center telemetry, all the information that we gather from all the machines, right? The cons of this approach that we've run into is sometimes diags are just too far removed from the metal, right? You get weird Jesus failures, things like that. You really can't tell what is happening. When the diag can't tell what is happening, we can't send a signal to our repair systems, right? Now, we've worked around that in some ways by, we know that the absence of information in certain ways, or sort of a superset of the absence and presence of information, still indicates, particular repair or failure, repair scenarios and failure syndromes, right? But that's not ideal. In some cases, a failure to respond of Jesus for various components, don't leave us a lot of information. I covered that. The other downside is Jesus is large and it's really complicated, right? We're looking at probably 2 or 3 decades of SWE work inside of Jesus, right? So it's typically not fully working. Fully working meaning like everything's 100% there with all the RPCs we support until well into an MPI cycle, right? This sometimes puts pressure on my team where we almost need to create 2 diag sets, right? One that's useful for like early bring up and validation testing, and then the second set of diags that's like really well integrated into the data center and the repair operations and all of that, right? So in some ways, it forces us to bifurcate our work a little bit. And then the other challenge that we have right now is, our hardware model, those dev paths that I spoke of, that's not really an industry standard in any way, right? That's very, very proprietary to Google. We looked at sort of the model that Redfish exposes, and it's close to what we need, but in some ways it's a bit more of a logical model in some ways than a physical model. So we're looking at ways that we could extend that and then basically hopefully use that for the same purpose of what we've historically been using our dev paths for. This is one of the paths forward that we're looking to go. as we try to get more and more industry standard with what we're doing here. So I just wanted to go through some quick example GSys commands. Like GSys CPU info, this is sort of the information that it's going to return, right? And there's all kinds of other flags where you can get information. But a lot of times this is just, combining together things from CPU info, info from sys/EPU, and other sort of platform specific items, right? Disk information, sort of the same thing, right? Ping all the disks, find out if they're alive, you get back all the LUNs, you get back all the physical connections, all of that. For PCIe information, you get back, basically what is the bus, some various register values. I think those are the AER registers. I'd have to look. The speed, what's the width, and then you also get downtrain information and things like that. Sensor list is all the telemetry we get back. This is generally power information, thermal information, fan speeds. For instances where we may be using water cooling, it's statistics concerning that. That's some of the information that we would get back from sensor list. Fans, we talked about a little bit. Usually it shows what their current RPM is and where they are in the duty cycle. We use this to try to find, fans that are not like the others. Hardware inventory, finding all the parts in the machine. And finally, I didn't mention this, event logging. So events are logged in a lot of different ways in some of our machines. In some cases, it's a BMC event log. In other cases, it's a proprietary EC event log. In some cases, it's just a kernel event log. GSys kind of abstracts all that away, that we have one sort of consistent event log. You can almost think of it like Collect D, the open source event log collector, if you've ever used that. It does a very similar function there. And that's sort of a summary of GSys, an overview of how we use it and where it fits into our diags. Right now, if you were to get the majority of our diags, if we open source them today, they're going to have dependencies on this layer that we can't open source, right? So we're looking to move around it, but that's one of the things that I wanted to talk about a little bit because it's going to impact our discussion around BIOS diagnostics, also going to impact our discussion even around PCIe. And Paul, I've got some stuff to talk about if we're going to touch that topic today too. But this sums up the GSys presentation here. Any questions?
Hey, Dan, quick question on great presentation. Let me actually turn on my camera. How do you deal with a case where you have a host proxying a system that may not have a running OS? Is that actually in the scope of GSys?
It is. So we have that challenge. So GSys, we always represent everything at a machine level, right? And our machine might consist of 0 or more sort of like host OSs, right? Like if you think about what do we consider a machine, there might be 4 or 5 different what we call arenas, right? And an arena is essentially a root of trust. So typically it consists of some type of BMC or something performing a BMC function, some type of device for attestation, right? Something to trust the firmware that we have installed. And then finally, the operating system running on top of that. And that operating system might be inside the BMC. It might be running on, a typical server, or it might be a level of abstraction above the typical server where really we have multiple servers all running, but we want them to look like one machine. And that would be where we get into more of the high performance computing and supercomputing space, right? That would be typically, our ML systems and things like that would fit into that category.
Got it. Okay. And one quick other question is, in building GSys or developing it, did you ever contrast it with the project from INRIA called HWLock? Did you ever talk about
I have not. I've actually not heard of HWLock, but I could query the GSys team and see if they looked into that and that, inspired the design. I don't know. Let me take a note of that, though.
Cool.
HWLOCK?
HWLOC.
Okay, got it. Oh, I'm sorry. I am familiar with that. No, and I don't think that that was looked at.
Okay.
And Dan, I was going to ask you, you mentioned that it's quite often not available early in NPI, so am I to presume that this is really meant to look for defects post the design phase, and you have different tools that you validate, a new platform, bring up, all that sort of stuff, and therefore this wouldn't include tests that are architectural compliance or fit and function necessarily. They're more looking for defect mechanisms, right?
That's generally true. I would say that's not our desired state. That's the state that we're in right now for the reasons you mentioned, just because it's a little late in the game sometimes. And really, the thing that makes it late in the game isn't so much like accessing the hardware information and things like that. A lot of times that will just work. Those dev paths are based off of a concept called our machine shape. And that takes a while to come to fruition. And really, Jesus doesn't work until that machine shape is there. I'm not an expert on this topic, but they have a hardware definition language, which is sort of like a giant, for us it's a proto, but it could be like a JSON or XML config file that says how do all the different devices in the machine connect together. And then ultimately that gets applied with another layer, which then attributes all the sensors, telemetry, and everything to that model. And that is like if you were to look at the swim lane diagram of all the different groups within inside of Google that are involved in bringing that together, it's really complicated because it hits, supply chain, it hits the design team, it hits the diagnostics team, it hits the data center team. And there's a lot of like litigation that goes on between the different groups as that comes together.
Yeah, so that would be structurally equivalent to the bill of materials topology type information, and yeah, I can see how that's kind of complex.
Yeah, it does get complex because the bill of materials will have some of the information, but then Jesus also goes down below like the bill of material level, right? When you get into like individual sensors on a motherboard or something like that. So it is that combined with a lot of other information as well, but that all comes together to a machine shape.
Yep, interesting. Thank you for the presentation.
Yeah, the other alternative to this approach that we've thought about is like, what could you do at, say, an ML process or a more generic mapping process where you try to separate these two things where DIGs know about like sort of physical or hardware properties that you then map into a model somewhere else? This is something else we're trying to explore, but we're not really sure that's fixing the problem. We think it's probably just moving the problem. But it does really address the problem of, well, Jesus isn't ready, so I need to create two diags during NPI, right?
Yeah. And just to poke at one more, the fact that you pick a topology that is tree-like presumes that that's the only topology. But in fact, we've found certainly, map out the PCI tree, for example, and then you look at the power domains, and they overlap in a nonlinear fashion. Or you'll look at the way that the IPMI commands flow across the hardware, and they don't follow the tree. They do something else. And then you have SM buses running around and things that are orthogonal to the tree. So are there structures in which you have to do kind of a special case awareness of relationships that GSys doesn't map? Or is there some additional mapping in GSys for sort of the non-orthogonal topologies?
For the most part, all of the mapping is inside Jesus. Now, for some of the things you mentioned, I'm sure there are edge cases in Jesus where, like it's doing like a graph traversal algorithm and it says like, hey, if you see this, stop and don't use the algorithm. I'm sure that that's in there, right?
Yeah.
That's sort of the histories of, technical debt that's going to be in that. But for the most part, it does a pretty good job. In addition to all the things you mentioned, there's also circular paths, right? Like where really you run into like toroid topologies and things like that. When do you stop walking the graph, right? Like if you look at Jesus, it's really it's a computer science lesson in graph theory. It's incredibly complicated.
And what about firmware in all of this? Does GSys stay out of firmware and stay close to hardware only, or does it have an interface to the firmware?
It's aware of firmware because like we have through information, and generally we want to install or verify the firmware that's on the through. And Jesus also plays a role in our attestation chain as well. It's not necessarily a source of truth, but it does provide some layer of the attestation layer. So it does have some information about like the firmware that's installed. And for diags, we leverage that to determine whether or not we need to update firmware. Even though that's not a diagnostic, we still refer to it as a diag that updates firmware.
I see. Thanks.
Hey Dan, great presentation, and I have a question to the entire audience. And I know for the past few months, we have been discussing on various tools that Google uses and Facebook uses from Forward to Voodoo to and all this. And this is again a great tool that does so many things. The thing that I get worried about is I feel challenged is some of these tools are internal to the organization, right? And they are not open source yet. Or I think the end goal that we are looking is how we can use these tools and test against hardware platforms that we have in our marketplace. And eventually, I think that the way we look at the things is that we would like to certify, those hardware and say, hey, by the way, these are the test cases that we ran against this hardware, and these are the test results. I think that's the end goal we are looking for. Now, the question that I have is that what exactly is the end goal? Is the end goal is that we are currently looking for different options, different tools that are available in the market? I think that's the
No,
first goal.
So the way I look at it is this: what we're looking to do is provide a set of common diagnostics for us that we can both use internally, and then we can also give to potential OCP hardware suppliers that you could say, look, if you run these diags and they're compliant and work properly on your hardware, there's a good chance that OPC members are going to be able to use that as is, right? That's one of the things that I'm looking to get out of this. The reason, or sort of maybe to address your question, the reason I bring up Jesus is I wanted to give the group a little historical context on why it's been somewhat difficult to fully open source some of our diagnostics, right? Here's a really good example. If you look at SAT or MemTester, right? These are two things. SAT is the stressful application test. That's something that we've open sourced, and then we've made a lot of recent changes to MemTester to multi-threaded, speed it up, things like that, right? We've committed those back to the community, but they're not exactly what we use internally, because what those two things are really doing is they're creating the load. In the case of MemTester, it's creating the load and looking for miscompares as well. But what MemTester doesn't do, for instance, is it's not looking for system events like uncorrectable errors or correctable errors or things like that. The only thing MemTester by itself would catch is miscompares, which do happen, but they're infrequent, right? If you were to look at our version of MemTester internally, it would be a combination of what we have open sourced and then what we have also kept as proprietary, which is sort of using Jesus along with it to basically go find the correctables and uncorrectables in addition to the miscompares. And then when a failure occurs, we take the physical memory location where it occurred, which MemTester can tell us. And then Jesus has the smarts to go all the way down through, say, the virtual address tables to the lookup tables to all the different things down to get to a physical DIM address, right? So I think the path forward here is for Google either really two things. Either one, we stick with that approach, right? Or we move some of these things over to something that is open, like the model that's exposed via Redfish. But right now, like we don't have drive telemetry and things like that in our Redfish or BMC information. Or the alternative approach is we just ditch this hardware abstraction layer and we start writing to the Linux level, right? Something like PCIe crawler, right? I was thinking, like, when we were having this PCIe discussion, I was like, well, if we got rid of Jesus, what would it mean? And what it would mean is that we'd be able to get everything that's in sysfs now. And then I would also say we would probably modify something like PCI crawler to also pick up the AUR register so that we can get error information as well. If I remember correctly, that tool at the moment is more looking at sort of like template and configuration. I think we could add those other properties to it. They would still get returned in that JSON structure. And then we could say, okay, now we've got a shared diagnostic that we can all kind of use and take advantage of. If that makes sense. I rambled on. I think I answered your question, but let me know if I didn't.
Very helpful. And I just have one follow-up question. So when you shared the information of, as an example, GSys to the suppliers, will you also share the test cases that the supplier has to run for GSys? Are there any test cases associated with GSys, or is it just a command line tool to perform certain operations?
Well, there's two cases, right? In one case, we have diagnostics that are using Jesus via the RPC, right? In that case, we just say, hey, suppliers, here's our diags, run these diags, right? We also give them really there's two options. We have a test executive they can use, which automatically captures all that information, and there's nothing you need to do because those diags spit out JSON, right? Or they could say, hey, look, we'll collect the JSON and use our own test executive. That's viable as well. There's another set of things where they may want to use Jesus without necessarily having a diagnostic that goes along with it. And I think the main use case for that is they're using it to check like which firmware version is installed on things. They're checking to make sure that the PCIe maps are programmed properly on devices. Like we don't do that with diagnostics now. We sort of let suppliers do that, but a lot of times they do leverage Jesus to do that on our machines. In some cases, there's huge overlap with what you could do with something like IPMI tool and Jesus. In that case, I think they will use IPMI tool, right? They know it, they love it. There's no training, there's no global dependencies, and that's great for us. In other cases, though, it gets a little complicated, and it's just easier for them to use Jesus.
Got it. That's very helpful, Dan. Thank you so much.
Rajiv, I'll add one more thing into this. Is that I think it's worthwhile to explore these options as possibilities, right? Like where we can build some commonality across the industry in terms of having a standardized platform or standardized method into getting these diagnostics.
Right, Paul, and something I think we both need to talk, and I totally understand that we're looking for commonalities, but the end goal is to deploy all these commonalities or the tools of our choice onto our existing OCP hardware platforms, so that the end user or the adopter can get more information of those hardware that hey, these tools have been run against them, and and these are the test cases that were run, and this is the pass fail result. And I think this benchmark or data would be very helpful for an adopter to look at before they make any decision. In fact, we can have some certifications where, hey, as an example, let's say Bryce Canyon, said certified against these testing validation tools, and here is information if somebody would like to get more detail on it. So that's how I see it. I might be wrong, but I would like to share everybody's thoughts on how do you guys envision when we find a commonality across the board.
I think we've had this discussion previously as well, and I think one thing that the team talked about was maybe even creating like an open source repository for benchmarks and things like that, like just having a location where you have these benchmarks that the results are coded and signed and uploaded to a specific site where everyone can see what your performance is, and then you kind of know what your own performance versus what the expected performance in the industry is. So
exactly, I think we need to do that. We need to do that. And actually, Dan shared a brilliant idea, and that was my question too: is whether the ODMs will have these tools. It seems like they will have access to these tools so that they can run these tools against the hardware that they're going to manufacture. So that's another use case as well.
But you always have sort of the decision to make on whether you want to open source the tool or the specification, right? So when Dan was talking about the hardware definition language, that could be a spec and an interface that any other team would take on implementing too. And so one question I kind of was thinking about is GSIS itself doesn't need to be open sourced, but if what it outputs, going with the redfish analogy, if what it outputs is defined a spec that could be open source, that in itself could be a huge contribution, because then, whatever hardware abstraction libraries we have or layers we could write glue between what we export and that specification. But also one other thought I had to your point, Rajiv, is in this discussion around open source, are we looking at it from sort of a Linux perspective of contributing modules into a larger sort of open source ecosystem where we may keep some proprietary information and say, okay, this is just going to be the Google contribution that nobody can peek into, but it abides by this specification. And as a result, when you provide that to a vendor, it is just a binary that nobody's expected to open up, even if it's in an open code like Python. But contractually, they wouldn't be given permission to modify. And I think that would be an interesting point to dig into with this group is, what are the limits of what we want to open source? Is it the entire repo of code that makes up a solution, or is it going to be limited by a specific set of interfaces that we want to define? I'm very curious about your thoughts, Rajiv, on this and others' thoughts.
Great discussions, and let me start it. And that's exactly I wanted to get us discuss this eventually at some point. So to address your first question, yes, I mean, if you have the specification available, and it would be very easy for others to take the specification and further enhance and build around it. So, and if there is enough interest in the community where you folks say, what, I think I have all the tools, all the APIs, I can build around it and make a complete tool set. Absolutely, yes. Number one. Number two is it's very difficult where you are building a software solution and you are contributing it to OCP, and 100% of the software is a source code, and there is hardly any binaries. In the real world, it will never happen because you have so many dependencies on other binaries, on other DLLs or SOs and whatnot. So it's totally okay if you have, let's say, 25% source code, and even the remaining 75% is a binary, where, let's say, Google, as an example, or Facebook, do not want to disclose about the contents of those binaries. That's still a very acceptable solution, where once we adopt that binary in our GitHub, and then our adopters use it, they are still using it. They are still getting some output from the binary. That's an acceptable solution.
Yeah, I think honestly, where I would really like to go with this is, as much open source as we can. I can say for Google, for us to run an opaque binary in the data center where we don't have source code for it, it's a major ordeal. There are examples where we do it, but like the level of hoops and whatnot we would have to jump through to enable that are non-trivial, right? We really do like to have a lot of insight, all the way down even to the driver level, right? The one question I've got for the team is, I agree with a lot of the discussion here. Obviously we can define APIs. I think when we originally started out, and I thought this was a very fruitful path, was trying to say, well, look, we've got diagnostics test things. What is sort of the output format we want to standardize on, right? But the one requirement we have that I don't think is unique, but I'd like to pull the room, is, our DIAs can test the hardware, but in order to integrate in with our larger data center systems, there needs to be like a well-known string, essentially, that identifies what is the hardware we tested, right, that we're recording our results against, whether that be a cable or a CPU or a FRU of any other type. Do other hyperscalers that are on the call here also have a similar requirement, or are you doing it differently? Maybe we're looking at this problem the wrong way.
Yeah, Yeah, my short answer, it cut off for a little bit, but is absolutely, yeah, the source of truth problem, if I got this right, Dan, to some extent, is very real. Maybe, so I mean, the short answer from my point of view is yes. If I understood the question to be, what is also the format of the source of truth of what it is that we're testing.
Yeah, I think it is. And if you look to the Windows world, this is a solved problem, right? They have device manager, right? Like it nails every single communicable device in the machine. In the Linux world, it's a lot more fragmented, right? There's not really an equivalent of something like a device manager that I'm aware of, anyway. I think that's what Jesus was really trying to be when it was come up with all those many moons ago.
Yeah, I'm trying to draw a parallel between Jesus and sysfs, and like it probably draws like a lot of similarities like between sysfs and pulling out IPMI data or BMC data, and combining them into a standardized platform, right? And I kind of see that objective to standardize the way we identify all these different components. Sorry, because I know I cut you off there. But yeah, I'm kind of curious about this as well, because traditionally, like I think sysfs has been developed quite intensively over the past couple of years, right? So um, it's been getting there as a system kind of tree where you can look at different devices. But yeah, Vincent, I know you had something else to add. Please go ahead.
I was just going to bring back Bill's point about the BOM, right? Because there's definitely that trifecta between your PLM solution or your BOM, your hardware definition layer, and your actual system reads, and take whatever is programmatically coded on for a DIM not matching what's actually on the label or what's actually recorded in a PLM system, and sometimes you have to make decisions that are going to be, you're expected to write code that checks something that's incomplete by definition, and those are the types of problems we deal with, right?
I think it's also not that we're recommending any particular path, but at Facebook, we have a separate system that validates the parts are there, they're the correct parts, there's the correct quantity, all that sort of stuff, separate from are they working correctly. And there's precedence and priority and things like that, so that we don't check to see if a part's working unless we know that it's there. And so we have a hierarchy there that says, call out the part because it's missing is a different response than call out the part because it's broken. So some of our systems, I think, are a little more fragmented than perhaps the GSys approach. Again, as you said, 10 or more years of growth and organic change, and everybody's got a way to improve it, has made it what it is. But we do keep them separate, and it sometimes hurts because they get out of sync. But then they do count on the BOM as a source of truth, but they have all sorts of translations difficulties. And there is a mechanism to know exactly sort of a signature of a machine to say this is the hardware that was in it when we tested it. The harder problem is saying, is this other machine that we want to infer equivalence to the same? Well, it could be off by a bit, and we don't know if they're similar, right? The judgment, the human looking at it and saying, oh, it's a different vendor of SSD, but it's fundamentally the same architecture, everything else is the same, we're going to, consider it equivalent. Those kinds of things are not programmatically structured very well. And I imagine you have similar challenges with multi-vendor sourcing, and when is it equivalent? When do we have to treat it differently? Comes down to a lot of detail, a lot of corner cases.
Bill, the system that you guys have right now that you're using to kind of inventory the unit, right? Where does that live? Does that live on? Well, some parts of it have to live on the unit. Some parts of it could be up in the cloud. Like, what is the architecture of that look like?
The architecture for both systems today is that an executable runs on the machine, uses whatever hooks, tricks, backdoor paths it needs to do its job, and there's different modules for every device type. So you talked about having many tests. We have probably over 100 different executables. There's also a mode to run it remotely. If that machine is too sick to diagnose itself, we can remotely run to it. And if it has network connectivity, almost everything runs off the same source code. Then there's also notions to run everything remotely, where there'd be lots of little drones around doing nothing but running diags and presence checks on other machines. But that's not the 90 percentile, right? Most of what's going on is it runs on a scheduled basis. A daemon kicks it off every however often, and it just runs locally. Then everything's stored to the cloud. Source of truth is in the cloud, and there's a lot of exchange, a lot of APIs back and forth for storing that.
Okay, and when you collect like your telemetry, not necessarily from diags, just why machines are running, you're reporting temperatures and fans and all that good stuff. Do they try to tie to that same model right now that you use for the inventory?
Not
Same
really.
model, I mean. So those
They're
are disconnected.
they're very separate. That's actually a third whole realm. There are some tools in which they're integrated, and that depends on where in the errors, when over time they were created. Some were created as a single thought, and therefore the instrumentation and the diags are much more closely coupled. But for the most part, we add instrumentation as we see the need for it. We add diagnostics when we see the need for it, and they're very asynchronous.
Okay, thanks, Bill. And then one last question. For your executable that runs on the machine that you do the inventory right now, is it one executable for all the different machine types at Facebook, or is it sort of like one executable per machine type?
It's a library of, and
Okay.
then each machine type runs different members from that library. So
Okay.
basically everyone is written to look at the machine and say, do I need to do anything here or not? So it's done that way rather than having a grand champion that tries to know the source of truth and then call the right jobs. There's inefficiencies in that because the job has to stub in, look at it and say, nope, you don't have a 1970s era RAID controller, so I'm not going to look for any. But that's sort of the way it's structured today.
Okay. Yeah, no, that's very helpful. I think, what we're really kind of coming down to is I think, with Jesus, people probably smarter and that predated me, they chose to solve one big hard problem as opposed to solving many slightly smaller and simpler problems. That might not have been the right path, but it's sort of where we're at now. Concerning the discussion with sysfs, because sysfs is the closest thing to a device manager for Linux, right? I think the two challenges that we would have there are one, sysfs is very much a logical model of the machine, not a physical model, right? It doesn't necessarily equate well to parts, but we could look at extensions for that. Sysfs is very easy to extend, right? The other problem it doesn't solve is when we have the idea of like an aggregate machine above the Linux environment, like one machine that might be 10 different Linuxes together. You would still need some type of hardware abstraction layer there. We have some diags, although these diags might be out of scope for what we would be discussing with the OCP. They like run at that level, right? Almost at like the cluster level or whatever you want to call it. And those are probably our really interesting benchmarks, right?
Yeah, I think that would probably be something that would be built out further down the road, right? Like if you're talking about, multi-cluster or even rack level diagnostics in that sense, right? But I think for now, one thing I'd like to draw attention back to is really, I think we've started out this project, we've on the path of looking at like component level testing in terms of how we can build that confidence in individual components, right? So it'll be ideal if we could kind of look at that from that perspective as well, right? So if we target it from component level and build up on sysfs or HESYS, and then eventually tie all of this into that level where we're able to do testing at a L10, L11 level, that would actually be what I would assume the ideal situation for this. With that, I think, does anyone else have any more questions or any more discussion around the system manager type scenario in Linux or Jesus.
Yeah, I'm not sure if it was for everyone, but you cut out there for a minute, Paul. I don't know if that was just on my side.
Oh, I'm sorry. I was just mentioning. I think I was just asking if anyone had any other questions on Jesus or like a sysfs question. If not, we have about 6 minutes left, and I was going to actually wanted to swing back to the PCIe topic or the BIOS topic today. I think we have a bunch of people that wanted to kickstart the BIOS testing program from our side. Andrea and Jens, I know you guys had some idea about that. And I think, Rajiv, you were going to reach out to the OSF team about this as well.
Yes, Paul. In fact, we do have the call tomorrow, the OSF call, and I would like to, discuss that in that call.
Okay, cool. Andrea and Jens, do you have anything else to add to the BIOS program or?
Yeah, I have to say I'm sorry because today I joined very late and had a choppy connection all the time, so didn't really follow along this meeting. But I'll try to get a catch up later.
No worries. We can touch base on this next week, I guess.
Yeah.
If we're ready.
Sorry about that.
That's okay.
BIOS next week and run us back.
Yep, cool. Then back to your PCIe thing. I think you wanted to talk something. You mentioned that you wanted to bring something else about PCIe into this.
I was going to propose the path forward and see what the group thinks here. What I was going to propose is that we take. I would really like to have a reference implementation of things. I think that's more useful than the spec. The spec is very good as well, but I think the spec more covers like result formats and things like that. But to get there, I think it helps to have at least one reference thing, and we've made the most progress on PCIe. What I was going to propose is why don't we take PCIe crawler, because it's very generic. We could make the changes to add PCI Gen 5 support to it, and then also collection of the AER registers for errors and things like that it doesn't have right now, and then use that as the basis for our result format. At Google, we'd be willing to, put in the work on that. We wouldn't be able to use it because, we don't have a source of truth yet, but I think that would be a really good path forward for us to be able to proceed. And I wanted to see what you thought, Paul, and the rest of the team.
Dan, I'll point out that the AAR enhancement was actually sketched out, and I think it's going forward. So that may already be in the pipeline for you.
Fantastic. We're halfway done.
And I don't know if it fits exactly where you're going, but we have tests that utilize the internal version of PCI crawler to do PCI link speed and PCI link width checking, and they require no external source of truth because they're checking internal bits versus internal bits. Now, they do have an override because if the bits get coded wrong, we need to be able to absorb that. But that might be a template test case because it's simply exploiting it, the JSON output, scraping to the output, and seeing that configured settings match actual settings.
Yeah, I think so too. And then that'll give us like a real world example when we start going in and talking about the result format, right? And then the other thing that I think I can take as an action item is to look at all the diags we have that don't have a tight Jesus dependency. And then we could say, well, hey, if we want to get them into this format, like how much work would that be? And then all of a sudden we would have a body of diagnostics that we could use, right? I'm thinking things like, MLC latency checking and things like that between chip to chip. Like there's not really a big Jesus dependency there, right?
That would be actually ideal. Then that kickstarts our pool of diagnostics. So I think one thing we have to be very careful here is also like what can we open source? What are we bringing to this, right? So then I think on your side, like one thing that we would probably want to be very careful about is like how much of these diagnostics can we open source from Google? And I think one AI for me is I can probably throw together, I probably should start a repository point for us to start talking in these diagnostics once we have them, right? So I'll take that AI as well to create all the administrative stuff.
Yeah, I think ultimately our goal is to get things up, not on like Google on board or Google Get on board, whatever that thing is called, but to like GitHub where it's like truly open and, we've got actual folks, working on it, contributing to it,
Yeah, and I think that's a thank you for bringing that up, by the way. That's a that's an excellent idea to head down this reference route. So yeah, I think we could probably do the same thing at Facebook. I don't want to speak out of position, but I think Vincent and Yen, we can probably do the same thing here, right?
Yep.
Cool. Cool. If that's it, then I think we have our AIs for next week. We will be talking about the BIOS testing next week as well, so that'll be good. Also, if you haven't had the opportunity to join the Slack channel, please join it. It's there. It's a good place for us to kind of collaborate among ourselves asynchronously. So
Question: did you eventually go to the Open System Firmware Slack, or is the new Slack?
we haven't merged into OSF Slack or anything, but that I'll have this chat with you offline, I guess, because it's at the top of the hour. But yeah,
Okay.
cool.
One last question, Paul. I know we're out of time here. What's sort of the OCP path forward here that we want to take? Do we want to formally form a working group, or?
I can answer that question, Paul. This is DJ. Hi, Dan. I think the eventual goal would be to have some kind of an OCP project. So think about it, Dan, this way. We have security, for instance, which is a OCP project, which transcends all of the physical device projects, right? Like server, networking, storage, and others. In the same fashion, we anticipate test and validation to become a standalone project which can transcend across many different devices which are being built inside OCP. Maybe we will start at one area, maybe we will start at, let's say, server or one particular area, but at least from the vision and the mission point of view, it can grow into, hey, can we provide test and validation into something which is happening on the storage side, or can we come up with something which is going to help networking folks? So it will become a technology vertical project similar to security, open system firmware, and others which are in existence.
Okay, sounds good to me. I think that's the direction I'm thinking as well.
Yeah. And in fact, to add to that comment, this is just a quick 1 minute comment and then I'll stop. OCP storage team had a very good workshop yesterday on the data center SSD spec, which has been released into OCP. And there was a big chunk of discussion in the workshop on test and validation of these devices. So I have asked the storage folks to connect with this particular work stream because I think there are a lot of overlaps between what was discussed in trying to bring things in the open source on test and validation, which actually should be also covered by this set of individuals in this work stream. So this is just an FYI, and we will try to connect the dots with specifics by bringing right people into this conversation. Thank you.
Thanks, Dharmesh. Thank you for raising that. Cool. If there's nothing else, we're at the top of the hour. Thank you everyone for joining, and I'll see you guys next week.
Thanks, folks. Take care. Bye.
Thank you. Bye.